Welcome back to the channel. I'm excited to dive into one of the most fundamental concepts in machine learning and data science today: Approximate Nearest Neighbor search, or ANN algorithms. Did you know that every time you search for similar images on Google, get product recommendations on Amazon, or even use facial recognition on your phone, ANN algorithms are working behind the scenes? These algorithms power everything from search engines to recommendation systems to computer vision applications. In today's video, we're going to demystify how these algorithms work, compare the three major approaches, LSH, Faiss, and HNSW, and I'll even show you how to implement a simple ANN system using Python. So grab your coffee and let's get started. Let's start with the basics. Imagine you have a massive database of points in high-dimensional spaces. These could be word embeddings, image features, or user preferences. Nearest neighbor search is about finding the points that are most similar to a given query point. It's like asking, hey, given this data point, what are the most similar items in my database? In a simple 2D space, this is straightforward. We calculate the Euclidean distance between our query point and every other point, then sort by distance. But here's where it gets interesting. In real-world applications, we're dealing with thousands or even millions of dimensions and billions of data points. A brute force search becomes computationally prohibitive. Imagine checking every single point every time someone searches. For n points in d dimensions, exact nearest neighbor search takes OND time. When n is in the millions and d is in the hundreds, that's just not feasible for real-time applications. This is where approximate nearest neighbor algorithms come to the rescue. The key insight is this: in most real-world applications, we don't need the absolutely perfect nearest neighbor, we just need something that's good enough. Think about it. If you're looking for similar products on an e-commerce site, does it really matter if the algorithm returns the first most similar item or the third most similar item? Probably not, as long as it's relevant. ANN algorithms trade off a small amount of accuracy for massive improvements in speed and memory usage. We're talking about going from minutes to milliseconds while still maintaining 95% accuracy in finding truly similar items. This trade-off enables real-time search across billions of items, powers recommendation systems that serve millions of users simultaneously, and makes applications like reverse image search practically possible. Now let's dive into the three major ANN algorithm families that dominate the field today. Each has its own strengths, weaknesses, and ideal use cases. Number 1, locality-sensitive hashing, or LSH. LSH is based on a brilliant insight. If we can create hash functions that map similar items to the same bucket with high probability, we can dramatically reduce our search space. The magic is in designing hash functions where similar points collide, meaning they get the same hash value more often than dissimilar points. Instead of checking all points, we only check points in the same hash bucket. Here's a simple example with random projections. LSH is simple to implement and works well for binary or sparse data. However, it can struggle with high-dimensional dense vectors and requires tuning multiple parameters. Number 2, Faiss, or Facebook AI Similarity Search. Faiss, developed by Facebook AI Research, is like the Swiss Army knife of ANN algorithms. It's not just one algorithm, it's an entire library with multiple indexing methods optimized for different scenarios. One of Faiss's key innovations is vector quantization. Instead of storing full vectors, it stores compressed representations. Think of it like JPEG compression for vectors. Here's how simple it is to get started with Faiss. What makes Faiss special is its GPU acceleration and production-ready optimizations. It can handle billions of vectors and still return results in milliseconds. Number 3, HNSW. Hierarchical, Navigable Small World Graphs. HNSW is perhaps the most elegant of the three approaches. It builds a multi-layer graph where each layer is a small world network, meaning you can get from any point to any other point in just a few hops. The key insight is creating shortcuts at higher layers. Imagine a city with local roads, highways, and superhighways. HNSW creates a similar hierarchy for navigating high-dimensional space. During search, we start at the top layer with the longest range connections, quickly get close to our target, then zoom in through progressively lower layers with finer-grained connections. While HNSW is more complex to implement from scratch, here's how you'd use it with the HNSW lib library. HNSW often provides the best balance of speed, accuracy, and memory usage, which is why it's become increasingly popular in production systems. Before we dive into choosing the right algorithm, let's cover some key concepts that apply across all ANN methods. Recall is the most important metric. It measures what fraction of the true nearest neighbors we actually find. A recall of 9.5 means we find 95% of the true nearest neighbors. There's always a trade-off between index build time, how long it takes to preprocess your data, and query time, how fast you can answer similarity queries. Memory overhead varies dramatically between algorithms. Some store the original vectors plus index structures. Others use compression techniques to reduce memory footprint. Parameter sensitivity is crucial for production deployment. Some algorithms need careful tuning for each dataset, while others work well with default parameters. This is the million-dollar question. Let me give you a practical decision framework based on your specific use case. For text and document search with sparse, binary features, LSH is often your best bet. It's simple, interpretable, and works well with high-dimensional sparse data. For large-scale image or dense vector search, Faiss is hard to beat, especially if you have GPU resources. Its quantization techniques can dramatically reduce memory usage while maintaining accuracy. For the best overall balance of accuracy, speed, and ease of use, HNSW is increasingly becoming the go-to choice. It's what powers many modern vector databases. Here's my quick checklist for choosing. Data size less than 1 million vectors? Start with HNSW. Need GPU acceleration? Faiss. Working with sparse or binary data? LSH. Need the absolute best accuracy? Faiss with IVF plus PQ. Want something simple and robust? HNSW. All right, let's get our hands dirty. I'm going to show you how to build a simple but powerful similarity search system using Faiss. This is the kind of system you might use for image similarity or product recommendations. First, let's create some synthetic data that represents image embeddings. Now let's compare different Faiss index types. Now let's compare search performance. Let's visualize our results. In real applications, you'd also want to save and load your indexes. Before we wrap up, let me share some hard-earned best practices from deploying ANN systems in production. Data preprocessing is critical. Always normalize your vectors for cosine similarity, remove outliers, and consider dimensionality reduction if you have extremely high-dimensional data. Parameter tuning strategy: start with default parameters, measure baseline performance, then tune one parameter at a time. Don't optimize for perfect recall. 95% is usually sufficient and much faster. Monitor in production. Track recall, query latency, and memory usage over time. Data drift can affect ANN performance more than traditional ML models. Plan for scale. Consider horizontal sharding for datasets beyond your single machine memory limits. Modern vector databases like Pinecone, Weaviate, or Milvus can help here. Handle updates wisely. Most ANN indexes don't support efficient updates. Plan your update strategy: full rebuilds, incremental indexes, or a hybrid approach. Wow, we covered a lot of ground today. Let's recap the key takeaways. First, ANN algorithms are essential for making similarity search practical at scale. They trade a small amount of accuracy for massive speed improvements. Second, choose your algorithm based on your specific use case: LSH for sparse data, Faiss for scale and GPU acceleration, HNSW for general purpose excellence. Third, the 80-20 rule applies here. You can get 80% of the benefit with 20% of the complexity by starting with well-tuned default parameters. I hope this deep dive helped demystify ANN algorithms for you. These techniques are powering the next generation of AI applications, from semantic search to recommendation systems. If you found this helpful, smash that like button and subscribe for more deep dives into machine learning algorithms. Drop a comment below about what ANN applications you're most excited about. I read every single one. Until next time, keep learning and keep building.